In weighty vertices, I'm given this undirected graph with non-negative edge weights and also vertex weights, right? I have edge weights here and vertex weights. And I have access to Dijkstra's algorithm that gives me a shortest path from vertex to every other vertex, given that they're only edge weights. But I want to construct a new graph such that I can feed it into Dijkstra solver and find the shortest path from the start vertex, right? Okay. So alternatively, we can get 2/3 credit for doing a directed version. So what I'm going to do is I'm going to start off with a directed version because it's kind of the easier way to go, right? Okay, so for a so the main point is that I need to somehow take this vertex weight and put it into the edges, right? Because Dijkstra can only take into account edge weights. So if I somehow go from this vertex to this vertex, this is 5, 2, and 1, then when I leave this vertex, I'm using this edge weight, right? When I leave it, I use this edge weight, so why not just add this into 5 here, right? So for all edges A and B, I add, so the distance of A and B is going to be equal to the distance of A and B from before, so distance prime, plus the weight of A, right? So this is going to force so if I visit A to B, when I visit B, I'm taking into account the weight of A that I'm using. So it's going to work if you add the other way as well, right? So when I enter B, you have to exit B, right? Unless you're the starting vertex and the vertex T, right? The ending vertex of the shortest path. When you enter this vertex, you have to leave to find that to an account for the path. So it doesn't really matter which weight you add it to, as long as you add it to one in one direction, right? Another idea is to, let's say I have A here, okay? 5. What I'm going to do is I'm going to take this vertex. Let's not use this. So I need to make this weight of 2 an edge, right? So that's exactly what I'm going to do. I'm going to take this and I'm going to turn it into an edge with 3. We have A in, right? This is an edge weight of 2 and A of out. Right? A in, I'm going to have all the incoming vertices of A, and A out is going to have all the outgoing vertices of A, right? That means in order to go from A in and A out, I have to take this edge weight of 2, which is the same edge weight as the vertex, which is the same weight as the vertex weight we have in A. So when I go through A here, I have to go into A in, go through this edge weight of 2, and then go through A out. So if I do go through A out, I would have accounted for the vertex weight of 2, right? So that's another reason why this works, is because I'm forcing, if I go through this vertex of A, I'm forcing this path to take this extra edge that I'm adding, right? Now, okay, this is only 2/3 credit, right? And I mean, we don't want that. So let's think about the undirected case. How can we build off this and make it undirected, right? This one way. I could just add a directed edge back here. But that does not necessarily work because remember, we only look at Dijkstra will only look at one edge once, right? If I add an edge back here and I'm like, okay, I look at this edge and then look at this edge as well, I can't just be like, oh, I have another incoming edge into A out. Can I take this edge again? No, not really, because I already looked at A out. I'm not gonna look at this edge again. So we don't want that, right? So suppose I have an edge here with a weight of 2, and I have these undirected graphs 5, 7, 3, and 1, right? I can't just be like, okay, A1, A2, and then make them directed, right? That's not gonna work because if let's see. If I split that and make it 1, it won't work either way because look, I pop up A1, I look at this edge, right? But let's say I never popped up B. I popped up C, I pop up A1, I look at this edge, I look at this edge, and then I look at B. I look at B, I look at this edge, but I update distance of A1, but since A1's already out of my priority queue, I'm not gonna look at this edge again, right? I can't just split them up like this. And I can't have an undirected one either, right? I can't, it's the same problem. I look at A1 through this incoming vertex, I look at all these outgoing edges, I look at this one, but now if I update A1 because of B, I can't look at this edge again, right? There's no way. I can only look at an edge once. So how do we solve this, right? So to solve this is, since we can only look at edge once, let's make an extra edge for every undirected edge I have, right? And in order to make an extra edge, I need an extra vertex. So for every one of these edges incident to A, I'm going to have a vertex for that edge. Essentially, I have A prime, A prime prime, A prime prime prime. Oh, it's 4 primes. It doesn't matter. Right? So here I have 3. So I'm going to keep my graph undirected. That's fine. That's no problem. 7, right? So now how do we account for the edge we have 2? Well, remember that since it's undirected, I can go from any of these edge through the vertex A to any of the other vertices. So I need an edge connecting to every one of these vertices, right? It becomes a complete subgraph, and this complete subgraph essentially becomes my old vertex of A over here. And every one of these has an edge weight of 2. Oh, I've done that. Right? And this solves a problem of the priority queue. Because in the priority queue, I visit 3, I pop up to A1, right? Now I visit this vertex, this vertex, this vertex. I've accounted for the possible shortest path to these 3 other vertices from A1. Now I look at this. Okay, this could be potential shortest path. Because I've never popped this off my queue, now I pop A prime prime off, right? I can now see, okay, could I make this a shorter path through this node after I just consider the shortest path through this vertex? And the answer is yes, because I now have this other edge that I could use to check whether I can update distance here, right? And as long as I enter this subgraph, I have to exit one of these. And as long as I exit, I have to take this edge weight of 2. And that's essentially the same as taking the vertex weight of 2. And it solves the problem of not being able to update an edge weight once I've seen it before if I just had, let's say, 1 split into 2, right? You want to, for every edge, I split it into 4, right? So let's generalize it. Kind of formulate this. For every vertex V, for vertex V, I'm gonna make VI. I'm gonna make these vertices VI for I in 1, 2 degree of V, right? And for every one of these VI, I'm making a complete subgraph. Complete subgraph between all VIs, right? And the edge of VI, Vj, the distance, is going to be equal to the weight of V, where Ij in 1 degree, this distance. Right. Okay. So in that question, I'm asking, okay, what about if I'm at S? What about if I'm at T? Well, it doesn't really matter. Right? Once you have the distance, you could just, like, if I'm leaving S, I don't actually go through S. So what you do is you just add the distance of S to all the shortest path that you finally obtain. And then, okay, you're asking, what if I enter this, I end the shortest path here, I don't actually take account the edge, the vertex weight. So again, you can add, so after I find my shortest path, right? So after dexterous algo, for every dist of u, this is gonna add the, what do you call it? The weight of s and the weight of u, right? For all u in vertices. So that's gonna be like, okay, if I'm leaving s and I'm stopping at u, I'm now accounting for those vertex weights as well. So it's a simple fix here. Now there's actually another solution for a undirected graph, and think about this. If I have a graph here, I don't do this, and I have an edge weight of a to b, right? So what we could do is we can add, make this 4, make this 2, make this 5. I'm going to add half of this edge weight into here and half this edge weight into here. And the reason we add half is that I have to add another half somewhere, right? Because if I enter through this edge into A, I have to exit somewhere. So if I exit through here, then the half here gets added to my shortest path, and the half here gets added to my shortest path. And in total, I'm going to get the 4 of it going through this vertex of A, right? And when I do this, so let's see. So now if I go through vertex A of shortest path, the half of these edge weights are distributed to both sides. And since when I enter vertex, I have to leave in my shortest path, somewhere in the middle, then together that's going to average out to my sum of the vertex weight, right? So let's see, my distance of AB is going to be the new distance prime is going to be equal to the distance of AB plus the weight of A over 2 plus the weight of B over 2. Now the question is, when I leave S, I only had half the weight in here, right? And again, when I'm leaving S, I only add a half the weight. And when I enter T, a vertex with the distance, I only add half from here, right? So again, we can do a simple fix like this. I now do for every edge in my new edge set, I'm gonna take the distance. Actually, let's not do. That's gonna be kind of weird. Let's see. What do we want to do? Okay, for every okay, so yeah, sorry. We're gonna take for every vertex V in V, I'm gonna update the distance of V to be the same distance of S plus the weight. So I'm going to take the weight of S, half of that, and the weight of V, half of that, right? So this accounts for me forgetting the half when I left S, and forgetting the half of the vertex weight when I entered V and I stopped, right? So in total, if I take this part and I add it into this, all I'm going to do is just remember to, yeah, no, that's fine. Just leave it right there. Yeah. So I'm going to calculate all of this distance like this by taking the vertex weight, split in half, and distribute to both sides to all my vertices. Right. All I'm going to do is distribute half of it to every. So all I'm going to take is you take that edge and you grab the half, the edge weights from both vertices, or you can think of it as I had this vertex A and I take half the vertex weight and then distribute to all of its edges. It's the same thing, right? But then at the end, I have to take all these distance values and I have to add half of the starting source node and half the weight of the ending vertex, because when I enter it, you don't leave this time, right? And if you don't leave, you're missing half. And so here are, let's see, 2 solutions for directed version and 2 solutions for the directed version.